Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
Matter as we know it is literally all the atoms, stars, and galaxies, the planets, the trees, and the rocks all around us.
I mean, it also includes us.
Yeah, and all of this, like including us, only account for like 5% of the known universe.
Yeah, because 25% of our universe is dark matter and 70% of it is dark energy, both of which are invisible to our eyes.
Yeah, that's kind of strange because it suggests that whatever we witness, whatever we experience every day is like a tiny fraction of reality.
Yeah, but it only gets worse. I mean, we have no clue about what dark matter and dark energy are or how they work. And we are pretty sure that they exist though. So, what do we really know about them?
Yeah, such puzzling mysteries. One would turn to Edward Witten for such questions, but that's of no use.
Dark matter is the stuff that makes it possible for galaxies to exist, right? So, when we calculated why the universe is structured in the way it is, it quickly became clear to scientists that there's not enough normal matter to compensate for it. The gravity of the visible matter is not strong enough to form galaxies and complex structures.
And if there would have been no dark matter, then the stars would have been more likely scattered all over the place, and they would not have ever formed galaxies.
Correct.
So we know that there has to be something else inside and around them that doesn't emit or reflect light. That basically something dark. That's why it's called dark matter and dark energy. At least that's what we think.
So, we have dark matter to thank for our galaxy.
Yes, we do.
Yeah, but besides being able to calculate the existence of dark matter, we can see it.
Huh, wait, what?
Kind of.
Okay,
There's a
okay.
catch, okay?
Kind of, okay.
So, places with a high concentration of dark matter, they can bend the light passing nearby them. And of course, this is in accordance with general relativity.
Yep.
Old Albie knew what he was doing, but sadly, none of us understood him when he was alive and in his prime.
Yeah, उसका दिमाग कुछ ज़्यादा ही तेज था ना?
Yeah, but let's not digress here, okay?
Yeah.
So, we know that there's something there that interacts with gravity.
Yeah.
And we should think a bit more intuitively. Just we need a little push over here. So right now we have more ideas about what dark energy and dark matter is not than what it actually is.
Yeah, we know that it's not just clouds of normal matter
Yeah.
without stars because that would emit particles we can detect. And dark matter is not antimatter like we've talked about anti-quarks in the first episode.
Yeah.
Because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, which are, I think, second episode, maybe third episode.
Second.
And they are like black holes are very compact objects with like high densities that violently affect their surroundings with the gravitational forces, like very high forces. And while dark matter seems is like scattered all over the place, so that's the opposite of black holes.
So basically to sum up,
Yeah.
we know only three things for sure, okay?
Okay.
So one, there is some kind of matter out there.
Huh.
Two, it interacts with gravity.
Correct.
And three, there's a lot of it.
Yeah, like 75, like 70, like 70 to 95%.
Correct. So dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in the way which we would normally expect. But right now, we just don't know about it.
And it can also be made up of like a whole new array of particles, like a dark standard particle model.
Oh.
And just imagine that, like a dark standard model of particle physics. Like we spoke about that, the standard model
yeah.
also. So, and each standard particle would have its own dark equivalent. Like it's intriguing.
Yeah, that sounds so interesting. But not forgetting about energy, I can say that dark energy is even more strange and mysterious because we can't detect it, we can't measure it, we can't taste it, we can't feel it. But we can see its effects very clearly.
Yeah. So in 1929, Edward Hubble from the Hubble Space Telescope, he examined how the wavelength of light emitted by distant galaxies shifts toward the red end of the electromagnetic spectrum as it travels to space. This is called a redshift, and we've spoken about this like many times in previous episodes. You can go check them out as well. So he found that fainter and more distant galaxies showed up a larger degree of redshift, and closer galaxies not so much.
Yeah, Hubble determined that this was because he theorized that the universe itself is expanding. This redshift occurs because the wavelengths of light are stretched as the universe expands. And more recent discoveries have shown that the expansion of the universe is actually accelerating.
Yeah.
Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and
Yeah.
collapse at some point.
Yeah. But space doesn't change its properties as it expands. There's just more of it. It's just like new spaces being created constantly everywhere. Galaxies are tightly bound clusters of stuff held together by gravity. So we don't experience this expansion in our daily lives, but we see it everywhere around our galaxy. So wherever there's empty space in the universe, more empty space is forming every second.
So, dark energy, it seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else that we know, and it only keeps getting stronger as time passes. Empty space has more energy than everything else in the universe combined. So ironic, isn't
Yes,
it?
very ironic. And we have multiple ideas about what dark energy might be. Like, for example, one idea is that it's not a thing but a property of space itself. Empty space is not nothing. Empty space has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that more and more space appears to fill the gaps, and that leads to a faster expanding universe as or accelerating universe as you said.
Yeah, so many question marks.
Yeah.
But this idea, the one that you spoke of, it's close to one that Einstein had back in 1917.
Old Albie is back.
Yes. It involved the concept of a cosmological constant, a force that basically counteracted the force of a gravity. The only problem is that when we tried to calculate this amount of energy, the result was so wrong and weird that it only added to the confusion.
So, you know what the interesting part about the cosmological constant is? It's believed that the unification of general relativity and quantum mechanics, like the two large scales, because general relativity is like usually on the scale of large bodies and quantum is all small.
Extremely small.
Yeah, for me, like
Yeah.
its length. So, the this like combination of general relativity and quantum mechanics will involve the calculation of the cosmological constant. That's what a belief is.
Yeah.
And the only theory that attempts to unify both of them is string theory.
Shout out to our friend Michio Kaku, by the way, who's among the bright minds at the Institute for Advanced Studies.
Yeah.
Yeah, he's hoping to figure this out. We hope he does.
Yep.
More power to you.
Yep. And physicists know that the rest of the universe, 95% of it, other than the normal matter, is the dark universe, which is only made of dark matter and dark energy.
But how do we know this? Well, we know because we look at things and we see them. That might seem rather too simplistic, but it is actually quite profound. Philosophy. Ah.
All the stuff that's like made of atoms is visible. Light bounces off of it, and we can see it. Simple as that. And when we look out into space, we can see stars and galaxies. And some of them, like the one we live in, Milky Way, are beautiful spiral shapes, spinning gracefully through space. But when scientists first measured the motion of groups of galaxies in the 1930s, they weighed the amount of matter they contained. And they were like really surprised because there's not enough visible stuff in those galaxies to even hold them together. They were like, how's that even possible?
Yeah, and later measurements of these individual galaxies confirmed this puzzling result. I mean, there's simply not enough visible stuff or matter in these galaxies to provide enough gravity to hold them together.
So from what we can see, they should literally just fly apart and like as we said earlier, they should just scatter. But they don't. So there must be some stuff, right, that we can't see and that's what we call dark matter. And currently the best evidence we have for it is the measurements of something called the cosmic microwave background radiation.
We've spoken about that before.
Yeah, high energy cosmic rays. Yeah. So the afterglow of the Big Bang, those rays, but that's another story for another episode.
Yeah, all the evidence we have here says that dark matter is there, and it accounts for much of the stuff in those beautiful spiral galaxies that fill the heavens. So, where does that leave us though?
Well, the discovery of dark matter took us one step further away from the center of things. It told us that the stuff we're made of is only like a small fraction of whatever the universe is made of, but there was more to come.
Early this century, scientists studying the outer reaches of the universe confirmed that not only is everything moving apart from everything else, as you would expect in a universe that began in a hot, dense Big Bang, but that they also found out that the universe expansion also seems to be accelerating.
Yeah, and what's that about, right? Either there's some kind of energy pushing this acceleration, just like you provide energy to accelerate a car, or gravity doesn't behave like normally, right, as we think.
That's where the dark energy thing comes in, right?
Yeah.
And most of the scientists think that it's the former. So today's best measurements allow us to work out just how much of the universe is dark.
And that leads us to the estimates of 25%
Correct.
dark matter and 70% dark energy that we spoke about earlier.
But the lingering question still remains is what is the dark matter made up of? What is the dark stuff made of? Right?
Yeah.
We don't know, but there's one theory which is called supersymmetry.
Interesting. Big word.
Yeah, it's called SUSY for short.
Susi Baka.
Yeah.
I mean, that could explain some of it, right?
Damn sus, if you know what I mean.
Supersymmetry basically predicts a whole range of new particles, as we spoke about earlier,
Yeah.
that some of them could make up the dark matter.
And if we found evidence for said SUSY, okay, I'm not saying that again. Supersymmetry.
SUSY.
Supersymmetry. If we found evidence for supersymmetry, we could go from understanding 5% of our universe to actually around a third. Not bad for a day's work, right?
Yeah, big improvement.
Yeah, and dark energy would probably be harder to understand, but there are some speculative theories out there that might point the way.
But with so much of the universe still like wanting to be explored, the stakes are high.
Yeah. Another idea is that empty space is actually full of temporary virtual particles that spontaneously and continually form from nothing and disappear into nothing again.
Yeah.
So the energy from those particles could be dark energy.
Yeah, this is like kind of this is what Hawking radiation is proposed to be. That one of these virtual particles and antiparticles gets sucked into the black hole, and like that takes the black hole's mass away from it, and that's why over like 10 raised to 100 years, the black hole finally evaporates, so-called evaporates into nothingness. So that's also related to black holes. We've spoken about it earlier, I
Yeah.
think.
And another theory is that maybe dark energy is an unknown kind of dynamic energy fluid or dynamic energy field which permeates the entire universe,
Wow.
but it somehow has the opposite effect on the universe compared to normal energy and matter.
Okay.
But if it exists, we don't know how or where or how we could even detect it. But
So we can see that there are a lot of questions left to answer.
yeah,
And our theories about dark matter and dark energy are just still that.
theories.
On one hand, that's kind of frustrating, right?
Hmm.
On the other hand, this is frontier science, and it's very exciting.
Yeah, it makes it so much more exciting. It shows us that no matter how much we feel that we're on the top of things, we're in the center of everything, we're still very much apes with smartphones, right?
Yep.
And we're on a tiny, fragile island in space.
Yeah.
And we're looking into the sky and wondering how our universe works.
Yeah. It's called the pale blue dot. We love hearing from our listeners and are always excited to dive into new topics.
You can reach out to us on quarktalkofficial@gmail.com at any time.